Next, let us welcome Mr. Aris Chen, the Vice President and General Manager of Delta Power and System PG. He will be talking about AI computing challenges, power, and thermal solutions. Let us welcome Mr. Chen.
让我们掌声欢迎
A round of applause for Mr. Chen. Dear colleagues, dear friends, good afternoon. I am the last speaker today. That means we are approaching the end of the session today. So please bear with me for about 20 to 30 minutes. So we've heard about AI ecosystem in the morning, and we talked about AI system in the afternoon. So I would like to take this opportunity to share with you the AI's back end, the power consumption and cooling solutions. So I think that this is a challenging topic for me to deliver. I want to use a simple and easy way to explain to you. I was actually modifying my slides yesterday. The organizer did not receive my latest slides. I really wanted to do this right. That is why I spent so many time honing my presentation slides. So we talked about a lot of issues. Mr. Lin just talked about cooling in his presentation. So I will also talk about our strategy and our solutions as well. These are my agenda topics. So AI computing power, AI data centers. There's the power supply and cooling challenges. Now, the second thing I would like to cover is from grid to chip. How can we provide an end-to-end power supply solution? And the third thing I would like to touch upon is how we can supply power with higher efficiency. So we are also thinking about how power architecture should look like in the new generation, and then I'll talk about cooling technology later. So AI data center has a huge demand for electricity. This is the latest statistics that we're seeing from 2024 last year. Around the world, AI data center consume 261 terawatt hours of electricity. So this is actually a massive number. Now, compared with Taiwan, in 2024, Taiwan used 283 terawatts of electricity last year. So last year, the total power consumption by AI data center around the world is equivalent to the power consumption of Taiwan for a year. So in the future, it will reach 300%, and it will be 500 terawatt hours in 2027. So if we can expand this to other AI data centers in the world, over the past 8 years, the AI data center has consumed 300% of energy from 2022 to 2030. So we are seeing that the demand has been growing, but the supply cannot keep up. So from chip to data center, the electricity actually goes through different systems before they enter the server. So when you stacked the servers and it becomes an AI rack, and then it will become a data center. It actually consumes electricity, right? So let's see. One server might use 2 to 10 kilowatt hours of electricity. And if you stack them together as an IT rack, it will consume 120,000 or kilowatts. So if you put them all together, that's 120 megawatts. That's the current status. In the future, the statistics will look like this. So the chips will consume 2,000 watts, and that's server for 15 kilowatt hours, and AI server rack kilowatt, 250 kilowatt to 1 megawatt, and AI data center 1 gigawatt. So if we compare this to household power usage, one data center is equivalent to 100,000 households' power consumption. So if you look at the AI servers, the power roadmap for AI servers, of course, will continue to grow with the power consumption. On the left side, we have the current status, and you can see that it's 120 kilowatt hours. So its voltage is from 2400 VAC to 54 VDC. And this year, we are working on GV300. And next generation, the voltage will be 200 to 800 kilowatt hours. So that's equivalent to, just imagine if you have a refrigerator that consumes so much power, what are we going to do? So in the future, if you have 54 volt, what can we do? So we need to try to lower this. So it needs to go from 54 to 800 volt. And then the rack will be 1.1 gigawatt. So 1.1 gigawatt. So let's compare this with some power plant numbers. I know that we are trying to phase out our nuclear plant here, but this is our nuclear plant 3. This is the generation capacity, 938 megawatt. So that's one nuclear reactor. That's equivalent to 938 AI rack. So if you have 1,000 IT racks, that's equivalent to the power generated from one nuclear generators. That goes to show power consumption will be the key challenge for AI development in the future. So what we are seeing is the hunger for electricity, and there's also many challenges. The first is power source, and the second thing is how can we increase the power consumption? Maybe we can work on power architecture and then power distribution. In addition to the grid, maybe the power distribution within a building is another key issue. Data centers often do not allow crash. So when we talk about 6.9, that we're talking about 6 nines, that means 99.9999%. But can our grid be that stable? I don't think so. That is why we need to have power. We need to have power backup. So when we have such a load capacity, the load will, of course, be connected to the grid, and the power supply quality will be affected as well. And sometimes you might even have blackouts. So that means demand outweighs the supply. So power quality. And then all of these electricity will become heat. How can we dissipate these heat? So I think that these are the things that AI need to address. In order to ensure smooth AI computing, all of these will have to be addressed. Let's now take a look at the infrastructure to power AI chips. From the power plant, power grid, data center, and then to AI chip. This is the power from end to end. On the left-hand side, you have two energy infrastructure. On the right-hand side, these two are the infrastructure of data centers. Our Delta products actually cover all of these four. So I will focus on data centers and AI chips today, and I'm going to talk about what we have done. At an AI data center, from grid to chip, we will see voltage conversion from high to mid to AC. and then it will be distributed across the AI data center. And then there will be power backup and the cooling solution. And the fifth one is IT. We do not have IT solutions, but data center also has to have IT solutions. And then there's data center on the service end. In addition to hyperscaler data center, we also have modular data centers. So we put them into a container. So all you need is water and electricity. This is called modular data center, and it will accelerate the deployment of data centers. And now, from the perspective of power supply, traditional power grid looks like this. At the power grid, within the building, there are AC. Now, please take a look at this small yellow ball here. That's the power entering into the building. We will have a transformer. We will lower the voltage from 220 to 400 volt. And then in the middle, there's the ATS. So it will switch. If the grid is off, it will connect it to the power supply. And then there's the UPS, and then we have IT rack. Our two previous presenters talked about these already. So we will change from AC to 50 DC. So we also heard about BBU, battery backup unit. This is our power backup. Recently, we have this latest technology called PCS, Power Capacitance Shelf. Later on, I'll talk about this. So basically, all of these right here are 50 volts. But when it comes to chips, we have to lower it to 0.6 volt. So once you complete all of these, it's from grid to chip power conversion. So it's 87.6% end-to-end efficiency. So that's 1 megawatt coming into the facility, the building. So 137 kilowatts of electricity is gone. They have evaporated into heat. So you have to remember this. Now, Delta offers a wider range of solutions. So we have the rack power, and it's one unit. It's called 1 RU or 1 OU, and it's 72 kilowatts. This is a figure that we cannot really put into perspective. 3 years ago, 1U server only consumes 1 kilowatt of power, but now 1U power will need 72 kilowatt hours of electricity. So you will see that they have different units. There's 12 kilowatts, and there's also 36 kilowatts of three-phase. And also there's the rack of the power capacitance shelf, like I talked about, PCS. So it's going from 50 volts to 0.65 volt. So we talked about PCS. What exactly is PCS? So basically, it looks like this. That's grid, transformer, and UPS, power generators, and AI server rack. So one rack, 120 kilowatt hours. So then, going through all of these, you will see 2 racks right here, the 10 racks right here, and the load is changing rapidly. So you will see that the power is reflected in the grid, and the grid cannot keep up. And what does that mean? So like I said, we have an UPS here. the capacity load is right here, so the volt is unstable. So the UPS will release electricity because it will assume that the power grid is off. And that means the battery of the UPS will be affected. So once the grid is off, you will have to rely on the power generator. Power generator, of course, will rely on motors. And then you will see that the motors will not keep up with this fast changing volts. So the power generators cannot keep up as well. That means you will be at risk of a fire. And then the power grid may also go off. So what can we do? Now there's the solution. We have an energy tank. It's called the capacitance shelf. So we will use this to adjust the power within the grid. For example, right here, there's the EDPC. That's the line in the middle. That's the average, the mean value. And you will see the fluctuations right here. So when it is up there, we will use this equipment to release that power. So when the power demand is at the bottom, we will let the electricity from the grid to come into right here. So it's called peak shelving. So what we are doing right here is that we can create a stable load, and this will create less impact on the power grid. The power grid will become more stable. So this is the technology that we have been using, and we rely on peak shaving. So we talked about efficiency. So that's the traditional AC distribution. And now the 87.6% is what we talked about. How can we ramp up this number? So that's 10 gigawatts we're talking about. If you convert it to kilowatts of power, kilowatt hours of electricity, that's 10,000 kilowatt hours of electricity every hour. That means a lot of money, right? So what can we do here is that we will reduce the number of power conversion. One conversion means one loss. So from the medium volt, 33 kilowatt, to 0.65 kilowatt, that means a lot of conversion. If we can reduce the number of conversion, the efficiency will be enhanced. So maybe we can think about using DC instead of using AC. So again, follow the path of the ball here. So from in the middle, we no longer use AC supply. We will have an independent power rack, 1 megawatt, one power rack that supplies 1 megawatt hours of electricity. So it's 800 volts right here. It's direct current. It's no longer alternate current. So this is called CDU, an 800 volt input. You have to have that to work with the system. So going through the power grid to 800 volt DC, so we can increase 1.5%. That's 89.1%. So that's 15 gigawatt. That's a significant saving. But is there a more effective way of doing this? So that's the second route. So all of these blocks have been skipped. So we concentrated them into this solid-state transformer. It's like using the 33 kVc to power electronics to reduce it to 800 volt DC. So that's one goal. 800 VDC and then will be distributed with PDU and PVS. We estimate that this will be 92% of power efficiency. So it's around 4.5% of increase. We think that this will be a huge help for the future power consumption. Now take a look at the power rack. So one power rack requires 1 gigawatt. So there's a lot of challenges and issues that we have to face. So the first thing is three-quarters of the rack is occupied by AI servers. There's no room for power. What can we do here? Why don't we move the power out? So in the future, power will have its own rack. There will be distribution board, and there will be power shelf, BBU, CPS, and there's comprehensive power solution. So it will look like this. AC will turn it into 800 DC, and then it will be supplied to the chips. So it's a comprehensive solution. Now I will not go into detail. If you look at the second route, the 91% route, there will be SST. So, like I said, it will be DC-DC on the right. So it's 6 megawatts. If you have 1 gigawatt, just imagine how many racks you will have. There's redundancy issue. You will have to have 300 racks to supply for 1 gigawatt data center. So power consumption is something we need to work on. So let's now move on to the cooling solutions. So Mr. Lin talked about the chip and IT racks. So we are focusing on the infrastructure level. So from the mid volts, you see every building having the liquid AC. So it will need the fan on the left. So once the liquids enters the equipment, we have the CDU. So there are two solutions. That's liquid to air and liquid to liquid. CDU for liquid to air, that's a water going into the rack. And then the CDU will dissipate the heat within the data center. And then there's liquid to liquid. So the water will go through CDU to the data center, and then the heat will be dissipated externally. That's called liquid to liquid. The PUE will increase significantly. So there are two solutions, liquid to air and liquid to liquid. And on the plate within the servers, and there's cold plates and vapor chambers. So from infrastructure to chips, all the cooling solutions are incorporated. So these are our products. All the racks are higher than me. They are more than 200 centimeters tall. Now in the middle, that's liquid to liquid, 1.5 megawatts. Like I said, one IT rack is 1 gigawatt. So right here, it's not enough. When you think about redundancy, you will probably have to need 2 racks. So this is actually a huge business opportunity. Now, I just talked about the modular data center. So if you want to build up your data center, it's not that complicated. Come to us and buy 1 rack. Everything is all set. Just simply drag it into the field that you want. You have water and electricity. Bam, it's done. So in conclusion, from grid, distribution, power backup, cooling solutions, IT services, and modulars. All of these are the product range of Delta. So allow me to promote our product here. So during COMPUTEX, we will have our booth from May 20th to May 23rd. Please come to our booth. I will be there for all of your questions. Come to me and we can talk about your concerns. So it will be L06178. That's our booth number. And I heard that it's on the fourth floor. I look forward to seeing you in our booth, and we can have more exchanges later. Thank you.